Hey, what's up, you guys? My name is Wish, and today we will be doing homework 5 problems. Okay, so the first problem is which register hold the address of the first location in the stack? So the question is pretty straightforward. Let's look at our options. The first option is stack pointer. The second option is instruction pointer. Third option is BX, which is a 16-bit part of register RBX. RBX is a 64-bit, or EBX, which is a 32-bit part of RBX, and DI, which is a 16-bit part of general purpose register EDI. Okay, so we have these 4 options. We know that the general purpose registers can be used for general purposes. They don't have like a specific uh specific tasks to do. They can be used for any general purpose things. That's why they're called general purposes. So this eliminates BX and DI. Now we're looking for the address of the stack. So we know instruction pointer points towards the next instruction that we're gonna that we're gonna use. So that doesn't do anything to our stack. So this means the stack pointer is the register that holds the beginning of the stack. So let's say you have a stack. Um, let's say you have this stack in memory. So like this, but you get the idea, right? Let's just say this is the stack. So the stack pointer will point toward this thing, this memory location, because this is the place from where the stack actually begins. Okay, next question. So our code segment is given, our instruction pointer is given, then we have DS and SI. Okay, we don't need what's the offset of the address instruction. Okay, so let's look at the how memory is. No, 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 that's the word. All right, so let me actually erase this and try it. Okay, so we know the code segment is 1401. So what code segment means, like it has sorry, sorry about that. Let's say the memory grows down like this and goes up like this. Let's just assume this is a part of a memory. Okay. So what happens is, in this case, for question number 2, I should have done this before. Okay. Let's say this is the code segment that we're dealing with. So we know that for this code segment, the address is 1401. So let's write that. And remember, whenever we deal with code segments, we always add a 0 after the last digit. So that's why I added 4101. Okay, so this whole segment has an address of 14010. Okay, that makes sense. It's like in a town, you have street names like Jefferson Street. So Jefferson Street just tells us this uh block of the memory that we're dealing with. Let's say if you have to go to my house, I'll tell you, like, I live in McFarland, let's say, and I live on the high street. So high street, like the street address, is basically like the code segment. Like it just tells you which block of the memory are we dealing with. Make sense? Okay. Then the IP CP, which is the instruction pointer, will tell you the exact address of my house. Okay, so in this case, let's say 1312 is somewhere here. This address is actually is right here. Let's just assume. So when we, like, for example, when I give you my house address, I'll tell you 3210 High Street, McFarland, California. So 3210 will be my house address, and then I'll give you a high street, which is the address where that house is located. Similarly, when we have to look for the location of a certain instruction in a pointer, we give it like this. We always write CS, which is the what code segment are we looking at, and at what instruction are we looking at. That's how we write the address of an instruction in actuality. But in this case, it's asking what is the offset address of the instruction to be fetched and executed. So it's asking us what's the house number of the instruction that we're gonna go and fetch. So in this case, we know 1410, which will be the address of this whole block, and 131210 is the address of the instruction that we're going to deal with. So it's asking what's the offset of the address of the memory location. So which is, in this case, it'll be 1, because remember, we write CP IP. CP for this case will be 14010, and IP will be 1332. So the offset address will be this. That'll be the address where the instruction is. This just tells us in which memory location is the address at, if that makes sense. Okay, next question. So we have everything is similar. What is the logical address of the instruction to be fetched and executed? So logical address basically means the whole address of the thing. Like, what's the actual address? So we know the address is always CS IP. So you can just write the values of CS 1401 with the address IP, which is 1332. That'll be the logical address of this question. Okay. Now it's asking what's the physical address of the instruction to be fetched and executed. Now let's look back here. So text. So we know this is 1401 block, right? And this is 1312. So the block right before 1401 should be 1400H. So let's assume that there is a block, memory block right before the block that we're dealing with. The address of that, the CS, the code segment address of that block gonna be 1400. Code segment address for this block gonna be 1401H. So it's asking us what's the physical address of that value. To find the physical address of the value, what we just do is we're gonna just, as I said, we always add 0 at the end of the code segment, then plus whatever the offset is, because think about it. So if this is 1400, this is 1401, so we know that every address in this block will have a street name of this or a code segment of this, but we are adding some offset to this, which will be the offset of 1312. So I can just write 2 equals 2. We can just add them. That will give us 15342. That'll be the physical address of this instruction. Okay, so I hope that makes sense. What are we doing here? So these questions were pretty simple, straightforward. Now the question fifth is, what is the lower range of the physical address of the code segment? So, okay, so we have the same everything. Let me erase everything else. So we know what are we dealing with. Okay, and this address is actually 1332. I messed up. There you go. Okay, so next question, it's asking us what's the, in this code segment, what's the last part of the, like, what's the physical address of the last block of the code segment. So it's basically asking us what's the address of, okay, how do I do this? Okay, I'm gonna just use, what's the address of this address? Like, what's the physical address of this block in this code segment? Okay, let's deal with this. So as we assumed in our memory location, if this block, if this block is 1401, then this will be 1400, right? Okay, so similarly, if this memory address is 1312, then the next one gonna be 133. Okay, I'm really bad at this writing. So the next address gonna be 1331, right? And the address right above it gonna be, right? Okay, and so on. So the address keeps on stretching like to the max, and this one goes to the bottom, like to the 000. So this means the farthest address of a code segment, a possible code segment, is always FFFF, because we're still dealing with hex. Okay, so this will be FFFF because that's how far a code segment goes. And this is one of those things that you have to memorize. Like, you need to know, like, in a code segment, the offset always begins from 4 zeros and it ends to FFFF. So this place will have offset of 4 zeros. I can just put it in here. So in a code segment, the offset goes from 4 zeros to 4 Fs. So in this case, it's asking us what's the physical address of this block, of this offset. So we can just simply say the physical address will be 1401 and add a 0 plus what's the offset of the last block, lower range, 000, right? So 1 2 3 4, which gives us 14010. So that'll be the physical address of the last block of the code segment. Now, what's the upper range? What's the address of this physical address of? Oh my God, my allergies. Sorry about that, guys. What's the physical address of this block? So we can do this again. I mean, 14010 plus, which will give us 2400F in hex. So that will be the physical address of this block. It's pretty straightforward. I hope that makes sense. Now on to the next question. Okay, if the lower range of the physical address of a code segment is FFFFEH, what's the upper range of, let's see here. Okay, so for this we will draw so let's try to draw this. So we have a block of memory. Okay, let's just say this, this, this. Okay. So if the lower range of the physical address of the code segment is FFFEH, so the physical address of this part is FFFF, right? That's the physical address. Okay. We have to find the address of the upper range. Okay. That's a good question. It's a good one. Let me double check if the address is right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So we know this that this one, the lower range of the code segment is 4 zeros. We know that, right? For sure, right? And we know that the upper range of the code segment is FFFF. Okay. So if we know the physical address of this, we have to find the physical address of this part. Okay. So what will we do is we can just add, so we know that from this place to this place there are like FFF entries, right? Because FFFF0 minus this will give us, what I'm trying to say is, so the how many blocks are there, we can just find it using this FFF minus this will give us this many entries in this code segment. So since we know the physical address of this entry, we can just add FFFF to this entry. So what I'm trying to basically say is if we know the physical address of this lower range, we can just add FFFF to the physical entry that will give us the physical entry of the upper range. That's what I'm trying to say. So that's what we're gonna do. So what we're gonna do is we can just do FFFF plus FFF. This gives us 10 FF. Okay. And we, for the code segment, we have like for the physical address, we have only 5 hex. We're just gonna write the lower, we go by the Little Indian standard, and we're just gonna write the first 5 hex. And this will be our the physical address of the upper range of the code segment. Like pretty straightforward, right? Okay, so the next instruction, next question 6. So we can just do this. We know the lower is no lower address has offset of 000. No upper address offset of FFFF. Total blocks of offset are FFFF minus 0.00000, which is FFFF. We just add FFFF to the physical address of the lower range will give us the This means f f f f e plus f f f f, which gives 10 f f d. But this one has only 1, 2, 3, 4, 5 hex values. We're just gonna take the little Indian standard, go from the bottom 5. There you go. Okay, next question. Complete the logical address of the instruction. Okay. So first thing first, we need to know a couple of things. So a move instruction like this, I mean, if you look at your book, I think it's in chapter 3. I think they have given that was chapter 3. Yeah, so they they have address generation, like for example, where's it? But yeah, like they have given these commands and they have told like what's the size of this command. I think I saw the one with there you go. So like for example, move AL to a number has a size of 8 bits, or like BL to 44 has a size of 8 bits. Like these kinds of stuff. It's in all in your books. Okay, so our question is, so we have these instructions. We know the logical address of this instruction, the second instruction. We are asked what's gonna be the logical instruction for logical address of this instruction and this instruction. Okay, so we know that we have 1034 11AC, right? So here 1034 is the code segment and 11AC is the instruction pointer. Okay, so what usually happens is if if this instruction is in code segment 1034, chances are the instruction right above it and right below it also gonna be in the same code segment. Reason being because 11AC. Okay, let's use our calculator. So 11AC. What happened? Oh no. 11AC. Okay. So 11AC is a 16-bit. It has a size of 16 bits. Okay. And we know that a single command like move 44 to some register is a 8-bit. So this means we just gonna change, we just need 8 bits to so let me explain this much better way. So we know that let's say there is 11AC. Let's just assume So we know that the command right above it, this means move AL A4, has a size of 8 bits. And since from zero from like okay, let me collect my thoughts to explain this better. Okay, so let's think of it this like this. So we know that the code segment is 1034. Okay, and the chances are the code segment gonna stay the same because these instructions are moving something to AL registers, which are lower 8 bits of AX. So this means each instruction is of 8-bit size, has a size of 8 bits. And uh, the code segments are like pretty big, pretty large. Like they go from 000 to FFF, and those are 16-bit addresses. So if we change 8 bits in those 16 bits, it won't change the code segment. It'll just change the offset. Basically, that's what I'm trying to say. So so you know what? I think I'm confusing myself and you guys. So let's just do the problem actually. This way it might make more sense when we solve it. So we know there's a something over here and something over here. Okay. And since these are just 8-bit instructions, they're not pretty large. And since 11 AC is like right in between somewhere here, like it will be, because it's like pretty far from 000, pretty far from FFF. So the chances are when we're changing the offset, it's highly unlikely that we'll move out of this code segment and go to some other code segment. It's highly unlikely in this case. So since we can just assume that the code segment gonna stay the same for both of the problems. And okay, now, so since we are just changing 8 bits of like we know that the size of these instructions are 8, right? So we can just do this. Hold up, where is it? Okay, I thought of the solution, how to explain this. Okay, sorry about that. It took me a while to collect my thoughts. So let's say this is the code segment, right? Okay, we'll draw the offsets in this code segment. There you go. Let's say this is the code segment and the address is 11 AC somewhere here. All right. Okay. So that's the line 2 instruction from the code. Now we have to find the address of the line 1 and line 3. Okay. So each block in the code, each block has a size of 1 byte or 4 bits. All right. So this means this has a size of 11 AC. This means this will be this will be 11 AB, right? And this will be 11 AD, right? Because we're just changing the last hex integer, and we know hex is 4-bit number, is a 4-bit. It has a size of 4-bit. One hex integer has a value of 4-bit. So since they're all like it's 11 AC AD AB, this means each block has a size of 1 byte. And in this case, we know that AL is an 8-bit register. So this means the size of this instruction is 8 bits or 2 bytes. So what we can do is we can just simply do 11 AC minus we're gonna go to. So let's say, okay, let's write this. So the last address is gonna be 000. We know that for sure, right? Okay, let's write this. It's gonna be 000 and FFF. Okay, cool. Let's do this. 11 AA will be here. 11 AE will be here. And so on and so forth, right? Okay, so we are at this location at this point. This is line 2, right? I'm gonna just write number 2 here. So we know line 2 is right here. And we know that the size of each instruction is an 8-bit. So the instruction right before this, so since this is line 2, instruction before it will be here, but that's only 4 bits. But we know this instruction is an 8-bit instruction. So we'll move this from here to here. This will be our line 1. So the address of line 1 will be 11AA. And similarly, if this is line 2, the next line 2 has a size of 8 bits and line 3 has a size of 8 bits. So this means the next instruction will be 8 bits away from this address. So this is 4 bits, this is 8 bits. So this will be our line 3. So the address will be 11 AE. Is that pretty straightforward? I hope this makes sense. Okay. And the last question. Okay. So we have two other errors. I guess my professor is grading for embedded systems. Okay. So for the next problem, I'm gonna just erase this, 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 and I'm gonna start. Okay, and next problem, we have an array of, okay. All right, so we'll remember this, and the array is like this. 0, 0, 0, 0, 0, right? That's the array that we're dealing with. Okay, and so what happens here? So this is just filling up the array with 10108. Okay, now the code segment. We're moving the offset of to EBX. Okay, so let's recall this. 1 in hex, or let's say 8 in hex. No, let's say A. This will make sense. In hex has a size of right. Give me a minute. Let me double check this. Okay. Okay, so here we go. Let's do it again. Okay, so we know that the array is 1010101010. Okay, and we know each block is a 1 byte, which means it can store 8 bits. So we know 1 in hex is 4 bits, A in hex is 4 bits, 0 in hex is 4 bits. So this means each block can store up to these values in them. 1 0 here. We're gonna go by little Indian. So the least one first. What do you mean? Okay, sorry. So the one block will save this 1 0 in itself. Then similarly, the next will be saved here, and the next will be saved here. Saved here. Saved here. There you go. So that's how these will be saved. So remember, these 1 0 are these ones. This is these two, and this one is these two at the top. Okay, so that's how these will be saved in the memory. So we know the first line says move the so EBX will be will point to the starting of this array. So we can say EBX will point towards this element right here. Make sense? Okay. Then we're moving 5040 to AX. So remember, AX is a 16-bit register. So AX will have 5040. So the upper so AX can be divided into two registers, AH and AL. So AH will have 50 and AL will have 40. This is important because each memory location is 1 byte while AX is a 2-byte register. So we have to remember that before solving this problem, because we're going to try to do some things to a 8-bit memory location with a 16-bit register. So that can be complicated. So let's just keep this in mind. So it'll be easier for us to remember. Let's keep this over here. All right. And this is another important part of our thing. And that's just an array. Okay. So what's the next instruction after? So we're moving 5048 to AX. We already did that. Okay. Now we are saying AX will move to the EBX. So EBX at this point is pointing towards 1 0, the first 1 0 of the array. Okay. And we're gonna move AX to this, but AX is a size of 16 bits. But this block has only is there a pointer here somewhere? There should be a pointer. Anyway, bud, I'll just use this. Oh my god. Okay, so AX is a size of 16 bits and each block is 8 bits. So we're trying to move a 16-bit to an 8-block thing, which might mess things up a little. So we have to be really careful what we're going to do. So since we are moving AX to this, we know we're going to replace this value for sure, right? So what will be the new value? So new value will be, since whatever the lower 16 bits are for AX. So this will be 40. Okay, this will be here in this place. And the top of 8 bits are 50. So we will replace the address right above this with 50. There you go. So this will happen after this instruction is processed. Does that make sense? Why? Because AX is a 16-bit register and we can only make changes to 8 bits in memory. So we have to do this in a way, if that makes sense. Okay, anyway. So the next line is increment EBX. So this means EBX gonna point to this part now. Okay, now what's gonna happen? We're gonna say move AX to EBX again. AX has still value of 5040. We haven't made changes. So the lower part of AX, which is 40, gonna be here. So it's gonna get replaced by 0 right here. And the upper half of AX will replace this 10. This means it will become 50. Make sense? Okay. So after this instruction, we're gonna increment EBX again. So EBX will point here. Okay, then we're gonna move AX to EBX again. AX has still the same value, so similar thing gonna happen. So we're gonna replace this 50 by 40. And this 10 will get replaced by 50. Okay, and then we're gonna increment EBX. So which means EBX will point towards here. And that ends the program. So this means the location 1 will have the value of 4040. Location 2 have the value of 5040. Location 3 will have the value of 1010. So there you go. That's how we solve these problems. And I think they're pretty straightforward. But again, if you have any question or any concerns, just shoot me an email. I'll try my best to help you guys. And thank you.